Typical floor deflection limits, some people say under total load, L over 240 is a reasonable limit. Some people say under live load, this is what we do for office buildings, we say under live load, and this is reduced live load, we say we are not going to let a composite beam in an office live load environment deflect more than L over 360 with an upper limit of 1.5 inches. Why the 1.5 inch limit? Well, we've been in situations where an office may have some very expensive millwork in it for that lawyer that's in the corner office, you know, they can afford all that nice millwork. And that millwork stuff has to be really level. If you got a floor that's doing this or doing that, that millwork is not going to come out right, and there are going to be some unhappy people. So we try to limit, based on experience, our live load deflection to 1.5 inches. Some people don't do that. That's up to you. Be careful of beams supporting CMU or brick wall or cladding. Look at Design Guide 3. They have some suggested deflection limits for these situations. Recommended limit at spandrel supporting cladding under live load, under live cladding and 50% of the superimposed dead load. I think Design Guide 3 suggests a deflection no more than 3/8 of an inch. That's to avoid those curtain wall problems. That's pretty stiff, and that's one of the reasons why you may want to consider not using composite action for spandrel beams and maybe making them moment frames out there. Reduced deflection also gets you some moment resistance or some lateral load resistance. Under live cladding wall load and 60% of the superimposed dead load, some people suggest L over 600 is a limit. So just think about that. Refer to Design Guide 3. Now let's talk about shear connectors real quickly, because it's been controversial over the last 10 or 15 years. And a lot of research occurred at Virginia Tech University under the direction of Dr. Sam Easterling. And AISC recently modified their shear connector requirements and basically lowered them slightly. And as I say, this is a result of a lot of tests and also a lot of comparison with the AISC spec requirements on shear connector capacities with what the rest of the world was doing. And we found that the U.S. had some of the highest shear capacities than any other country in the world. And that raised a few eyebrows and caused us to go back to the drawing board. We did that. And the whole issue of a shear connector in the strong position or the weak position came up. And during the test, it became very clear that if you have a simple beam, like shown here, and you have a composite slab crossing the flange, whether you put that stud in the so-called strong position, if you look on the right-hand side, the strong position would be the case where you put more concrete cover between the stud and the edge of the deck toward the center line. Sorry, my pointer just doesn't want to cooperate, but right here, that's the strong position, that's the weak position, and the shear force is going this way from left to right. Now, why does the guy put the thing in the strong position and the weak position instead of putting it in the middle? Well, the reason is the metal deck manufacturers have to have this rib. See that little bump there in the middle of the flute? That's the rib. It's a stiffening rib that gives the deck its additional capacity as a form during the construction stage. They need that as a stiffener, in effect. And they're not going to take it out because we already asked them. Sorry, we're not going to do that. So we're stuck. The guy in the field is going to say, well, I can't put the darn gun right over that flute, so I'm going to put the stud on the one side or the other. You tell me where you want it. Well, if we tell the guy to put it on the weak side, he'll do it right over, or if you tell him to do it on the strong side, he'll do it okay on half the span, but then he'll keep doing what he was doing all the way over to the end, and then it's on the weak side. So unless you're out there watching the guy to be sure that he flips it over, you know, to keep them all on the strong side, you as the engineer got to decide, do you want to tell him to put half of them on the weak side and half of them on the, or alternate them, so that at least you'll get 50% of them right? Or do you want to run the risk to say, put them all on the strong side, and then you might get them all wrong, because you may do it wrong. Your drawings need to cover this, and different engineers do it different ways. We generally say alternate them back and forth. And then we base our capacity of our beam on that condition because we know he'll probably get that right if you tell him to alternate them. I'd be real careful if you put on your drawings to put them all in the strong position. You better be sure he does it, or you could end up with not enough shear connectors for the live load capacity you're looking for. But anyway, during the testing process, we found that the strength of the connector was highly dependent on whether that connector was in the strong position or the weak position. And I think it's pretty obvious, right? When you have it in the weak position and you've got this big horizontal shear force pushing out, that stud is not going to be as strong and deliver as much shear as it would in the strong position. So that had to get factored into the new requirements. And Dr. Easterlin and his compadres there at Virginia Tech suggested a Q sub n equation that was basically the same equation as before as an upper bound, 0.5 times the area of the shear connector times the square root of F prime C times E. That's the old long-standing stud equation. But then we had to put some reducing multipliers on there to account for the strong position, the weak position, and a bunch of other factors. So the result today is the new 2005 spec gives you that is the new shear connector equation with an R sub G, which I say stands for stud geometry condition, as an adjustment factor. And then R sub P, these are terms that are in the spec now, is the stud position factor. These R sub G and R sub P values now take on reduction factors less than 1 that are now reflected in the stud capacity equations. And again, they reflect the stud in the strong position or the weak position. I'm just going to cover a couple of situations. These are covered in the commentary to Chapter I. Gets into this and tells you, matter of fact, the commentary, I believe, gives you a table now, just like the table I'm going to show you in a minute. It tabulates all this for you for the more common conditions. But if you put a stud in the weak position, as shown to the left there, the position factor is 0.6. If you put it in the strong position, it increases that factor to 0.75. So in R sub P is equal to 1 only for a stud welded directly to the steel beam with no deck. So this position factor is acknowledging that A, you have a metal deck there, and just by welding a stud through a deck, you're going to get a reduction in capacity over what you would do if you just had it welded to a steel beam directly. And depending on whether you put the stud in the strong or the weak position, depends on that, what the magnitude of that factor is. So that's R sub P values. There's also geometry, R sub G factor, and that takes the value of 1 if you put a single stud in the rib of a deck perpendicular to the beam, or if the deck is parallel to the beam with typical rib widths, and the specification talks about what's an acceptable rib width for the girder situation. You get to take R sub G is equal to 1. As soon as you put 2 studs or 3 or more studs per rib, you start taking on additional reductions. So with 2 studs per rib, R sub G is 0.85, 3 it's 0.7. So these two factors are additive in the sense that you apply them both at the same time in the stud equation. And the result is we generally are getting 5, 10 to 15% lower stud capacities than before. And our new specification then calibrates better with tests and also brings us in the U.S. in a little bit more alignment with what the other countries around the world are doing. Now you say, oh my God, I designed 4,000 composite beams last week. And I designed it by the 1999 spec. And wow, does that mean all my beams are in trouble? Well, the answer is no. One of the controversial parts of this was the fact that there really has been no reported failures or problems with composite floor construction in the United States that anybody on the spec committee was aware of. And so one argument was, why do we want to reduce all of our stud capacities when there's no evidence of any problems with what we had in the old formulas? That's a fair question. And I think there's probably some conservatism built into our composite beam design, because you get a lot of, you're designing a beam assuming it's a one-way element, and you're assuming a certain flange width, and you're ignoring the beam on either side of you. Well, in reality, you get some two-way action there that probably makes our model, our composite beam model, fairly conservative. So that's probably one reason we haven't seen any failures. Another reason is we rarely get floors loaded up to their factored loads, right? Theoretically, you wouldn't see a problem until you loaded the floor up with its factored live load, and that doesn't happen very often. Although any of you that know about these rolling file systems that are out there these days, you know that you can load up a floor real fast with a rolling file system. And for the life of me, I've seen law libraries on rolling file systems that have loaded up floors to 300 pounds a square foot when they're only designed for 50 plus 20, and they're sitting there deflected 6 inches, and they haven't come down. So there's a lot of robustness, I think, in our composite beams, which really makes it a pretty impressive element. And one reason why the fee factors are 0.9 is it's a very ductile element that has a lot of robustness to it. But anyway, the bottom line is we really haven't had any problem. But I think the spec committee ended up voting for this new model that's based on research and brings us again into alignment more with what the other world specifications are doing. But really, if you go back and check, okay, what is assuming I had 5% less shear connectors than I needed, going back to the old model, what effect does that have on my capacity? It really doesn't affect it that much. In other words, it's not too sensitive to the number of connectors. Now, you got to think about shear connector placement for girders. Obviously, for uniformly loaded beams, you just put them uniformly across the span. The AISC specification for years has said you can put them on uniform. You don't have to follow the shear diagram. For girders, though, you may want to think about putting a detail on your drawings which covers the 3-point loading condition, where you either put them on uniformly and upsize the number of connectors so that you put them on uniformly and get the number of connectors you want in the ends, but realizing that constant moment area in the section, you really don't need any shear connectors because your moment isn't changing, therefore theoretically there's no shear transfer there. So you just have to decide on your drawings how you're going to handle shear connector placement on your drawings in your typical detail. You need to know what your program is doing. Some programs would say, okay, I'm going to upsize the number of connectors, assuming you're going to put them on them in a uniform fashion so I get the right number at the ends. Some programs are only going to give you the number you need, and you probably should be putting, out in the outer 2/3 and none in the middle, or a nominal number in the middle. So just be aware of that issue. The shear connector spacing hasn't changed any. It's still the same as it's always been, 3D, 4D, and 6D as shown here. That's all the same. Should the number of shear connectors be increased over the calculated value? Again, in a matter of engineering judgment, depending on your client and your function of your building. Maybe you want to put some extra connectors in there in recognition of some of them may not be any good, or we may have a live load requirement change in the future where I want more capacity. I know we work for a lot of hospitals, for instance, that say we want full composite action and we want to design for 150-pound unreduced live load, end of story. And obviously you've got some flexibility in a floor like that. Be on the lookout, and we're going to talk about this more in the diaphragm discussion this afternoon, but be on the lookout for situations where you have drag beams or collector beams that are collecting shear, diaphragm shear, and delivering it over to your lateral load resisting system. There you may need some additional shear connectors on those elements to account for the additional shear that's in there from the lateral load resisting design, either seismic or wind. Usually it's a problem more for seismic. Connections and reactions gets to be an issue. If you delegate the design to a fabricator or you design them yourself, somebody's got to be told how to design the connections. Fabricators really strongly encourage us engineers to put the reactions on the drawings. Don't tell them to design for the load tables because it's generally conservative. So in our practice, we write the reactions on the drawings or we design the connections ourselves. Different ways, obviously, to handle that. The 10 kip LRFD load and the 6 kip minimum reaction load for ASD, that is no longer in the 2005 spec. Some engineers may want to still specify a minimum in their specs. But be advised that the spec no longer carries that as a requirement like it used to in the 99 spec. Again, we talked about how to specify the loads. The best thing to do is put the loads on the drawings so that the guy designing the connections has the actual forces, not some arbitrarily inflated force. And if you have axial loads in your members, either from diaphragm or basement wall reactions or whatever, also you should show those loads on the drawings so that the connection designer knows what the loads are. Should calculated reactions be increased? Well, you can make an argument both for and against that. Again, I think it depends on who you're working for and what his goals are as an owner of the building. So you can make an argument both ways. Now I want to talk briefly about this topic. This is one I think most engineers are really not very aware of. If you have a moment frame in a steel building that has composite floors, I believe that most engineers would design that moment frame as if the beams were non-composite. That is, they would take the moment of inertia of the bare steel beam, proportion the wind moments for that bare steel beam, and not count on the fact that that beam might be composite. Well, that's certainly conservative, but I'm going to tell you that I've never designed a moment frame in a steel building that was not controlled by drift. And I'll bet many of you have seen the same thing. Usually drift controls the design of a moment frame, either wind drift or seismic drift. So assuming that the moment of inertia of that beam is the eye of the bare beam is a very conservative assumption. And here to tell you there's a simple way to count on the composite action of the floor system in your moment frame drift calculation by using a moment of inertia that's higher than the bare steel beam. And this next series of slides was developed to show you how to do that. And we did this just in a spreadsheet. But basically the concept is we break the beam up into 3 zones. Zones 1, 2, and 3. Zone 1 is where the steel moment of inertia, you're in the negative moment region, so theoretically the concrete's in tension, right? It's not doing anything for you if it's in tension, right? So there is no composite action. So in that zone 1, you use the bare steel beam moment of inertia. And we're going to assume conservatively that that zone 1 is over half the span of the beam. Most of the time it'll be less than that, but we're going to assume it's over half. Region 2 is the area where you really got the slab in compression, and the slab and the steel beam are acting together, and you got a lot more moment of inertia there than you do with the bare steel beam by itself. So how can we take advantage of that? Well, one simple way and conservative way to take advantage of that situation is to use that lower bound moment of inertia we talked about earlier. The equation for the lower bound moment of inertia is given in the commentary to Chapter I. It's a simple equation. So we could put some shear connectors on there to develop that lower bound moment of inertia, and voila, we've all of a sudden in zone 2 have increased the moment of inertia of our bare steel beam probably by 15, 20, 25, 30%. And that could reduce our drift, our calculated drift, and therefore lower the beam size we need. The final zone 3 is the area right next to the column. And that's the point where it takes a little while to develop that moment into the slab when you're right next to the column. So in zone 3, we're going to say the effective moment of inertia is conservatively taking it as the bare steel beam. So with those simplistic assumptions, and again, those are very conservative, and here's that zone 3 we were talking about, where you come out from the center of your column, you draw a 45-degree line, and where it hits your effective flange width, that defines the length of zone 3. So now, this is all discussed in a nice paper that's referenced here that was in a engineering journal paper. So we didn't just make this up. All we did is use it and tabulate it in a spreadsheet and made some tables. But now, how do you do this? Well, you don't want to design a beam that has segmented with different moments of inertia. That's kind of a pain, right? So what we did is we said, okay, let's take the real 3 zones and take a sub-assemblage, which is half the beam span on either side of the column that goes halfway up to the floor above and halfway to the floor below. We call that a sub-assemblage. We put a lateral load on there, and we say, okay, under those 3 moment of inertia zones, how much does that sub-assemblage deflect laterally? And we get that number. Then we say, okay, let's simplify that. Instead of putting 3 zones, let's assume we have some effective moment of inertia that's constant along the span, and we're going to derive an expression for that effective moment of inertia such that it gets the same deflection here for that sub-assemblage as this more complex model did. Now we only have to input 1 effective moment of inertia for the span, and it's real easy to do that in your computer program. And now what we've done is we've increased the moment of inertia of our spandrel beam, or our moment frame beam, by probably 10 to 30%, and we've counted on composite action in the design of our moment frame. Now that's kind of neat because you get that for free. You really didn't have to do much of anything to get that. And as I say, almost all moment frames are governed by drift rather than strength. So that's pretty simple to do. You can find, you can do a spreadsheet. Go to that paper. You want to tabulate a little simple spreadsheet. Make a table for different slab thicknesses and composite decks and pass it around to your engineers. It's a real simple design aid to have. Okay, the last topic we're going to talk about here in this section on composite beams is strengthening of existing beams. Obviously, we've all been in situations where we wanted to increase the live load capacity of a floor from 50 plus 20 to 100 or 150 or even 250. How do you do that? Well, there's different ways to do it. But you also got to not only worry about the composite capacity, but you also got to worry about the connections and what they were designed for, to be sure you got enough connection capacity. So it's pretty simple to core down into a composite beam, weld a shear connector on there by hand, and then put non-shrink grout back in there to increase or add additional shear connectors or add shear connectors when you didn't have any before. That's pretty easy to do. There's a paper by David Ricker, who's now retired, but an old engineering journal paper that talks about strengthening of composite beams and also talks about welding to existing beams. I encourage you to read that as referenced here. How do you strengthen the beam? Well, you can either put a cover plate on there. Generally, if you do that, you want to make the cover plate wider, so this is a downhand weld. A stitch fillet weld will usually do the job. Or if that's not enough capacity, you can maybe weld a T down there. This one is a little bit more of a problem because if the beam has any existing deflection, then your T profile has to follow that. So in order to do that, you may have to put a little kind of a shear tab hanging down there to weld that to close that gap if there is a bow in your beam. But anyway, this is an effective way, either way, to increase the capacity by adding moment of inertia. Again, there's another paper by John Miller in the Engineering Journal article going back 10 years or so. It gives you an algorithm to design your strengthened beam for. Very simple. Gives you the equations for it. You don't have to derive them yourself. So I encourage you to do that if you don't already know about that. In all upgrades, critical strength limit may be the connection. So you got to delve into your connections. What are they good for? If many old buildings were designed for A307 bolts, might be a matter of shoring that beam, taking the A307 3/4-inch bolts out and putting in A490 bolts or A325 bolts. Voila, you got more shear capacity. Or it may be instead of a bolted connection, you got to go to a welded connection. So different ways to increase the connection capacity, obviously. If they use slip critical connections, maybe you can use a bearing connection in there to get more capacity. So there are different strategies there. So that covers the section on composite beams. And I'm going to open it up to questions on that now. Anybody has anything on that? Yes, sir. Here, take the microphone here.
I was working on an existing job building where they had a composite beam, but the end of the beam, the 4 feet of the end of the beam, had no slab on it. Is that considered a composite beam, or do you have to design those as non-composite?
If it's 4 feet at the end of a long span,
Yeah.
I don't know what your span was, 30 feet or
About 36 feet. Yeah.
36 feet. Yeah, you'll probably find that composite slab, you don't need it that close to the support. But the way you would check that is you draw the moment diagram.
Yeah.
You
And
get your moment capacity right there and check and be sure that for that moment diagram, the bare steel beam works by itself. If it does, then you're okay. But remember, you got to develop that moment a little bit past where your opening is. So you got to take that into consideration. But usually, if it's 4 feet only from the support, you don't have the moment diagram high enough where it's probably going to be a problem.
Okay, yeah, because most software programs automatically design them as non-composite.
Right.
And I was checking it was like adding additional loads to them, and of course I just wanted to make sure that
Yeah.
that it was the right approach to still consider that as a composite.
Okay, you only need usually the center of the beam is where you have the maximum moment, right? So that's where you need the composite action the most. As long as you can satisfy that, and then where it turns non-composite, be sure your beam is strong enough to carry the moment at that location, then you're okay. Any other questions? Okay, well, we're gonna one more. Here you go.
Did you mean to say that the engineer of record is responsible for going to the fabrication mill and check on the cambers?
Not the mill,
I mean,
the fabrication shop.
yeah, fabrication
No, he's
shop.
not necessarily responsible. All I'm saying is most projects are going to have a testing laboratory, right? That's usually hired by the owner to serve the owner's interest in checking the quality of construction. The engineer has certain job observation responsibilities depending on his contract, right? He may or may not be required to go to the job site. We generally want to go to the job site to protect our interests, but usually the way this would work is that the owner's testing laboratory would be the party in the fabrication shop checking this on behalf of the owner under a plan probably prepared by the engineer of record. But no, I didn't mean to imply that it was our job
All right.
to go to the fabrication shop and check all these beams. That's usually not the case.
All right. Thank you.
Is that right, Bonnie? Okay. She's my code expert over here.